Hey everybody, I'm Christian and this is First Principles. Today we're talking to Nato's Saichek about the physics and economics of Longshot Space, a company that's literally building a gun to launch stuff into orbit. If it works, it would get payloads to orbit significantly cheaper, maybe down into the single-digit dollars per kilogram to orbit. I think you'll love learning about the physics of Longshot Space. This is Nato's Saichek on First Principles. Nato, I actually remember back when we were working at Astranis, there was a time when me and you were at, it was probably like that cafe by South Park, like Cafe Strata or something like that.
Yeah.
And you were pitching me this like truly crazy idea about like a rocket that would use water vapor or something, or like it would use
laser
like
rocket.
lasers. Yeah. Tell me about the laser rocket. What was
Okay, so the basic idea with the laser rocket is that limitation on the efficiency of rockets is that all of the energy in the propellant has to come from the chemistry of your fuel and your oxidizer. So if you can decouple the energy in your propellant, the chemistry on board, then and you can put it onto the ground, then you unlock higher specific impulses, which lets you, have much more efficient rockets. So you have a giant bank of lasers on the ground, shoot them at your rocket, dump your propellant through a heat exchanger. And so now your limitation in how hot your propellant can get is how hot your heat exchanger can be. And there's a whole bunch of clever stuff you can do to make your heat exchanger ridiculously hot. And then you can get a rocket that has a specific impulse of like 800 seconds or something that's normally associated with like, Hall effect thrusters instead of, chemical propulsion, which means that your rockets can be much smaller, which means everything gets simpler in a lot of ways. And anyway, that was that idea.
I love that. I remember that conversation very well. And I think it's fun. So did you consider that for this company? Like, were you trying to pitch your co-founder on doing that before you guys landed on guns?
Yeah, we built a bunch of little things in a garage. We built little heat exchangers. We built microwave susceptors. We played around with a bunch of ideas, a few years ago. And I'll admit, I was very bullish on that. I thought that was like the way to go. He ended up coming up with this idea, and I was not that excited about this idea. I thought it was, I thought there were going to be way too many problems here, and it was dumb in a variety of ways, and I came up with a whole bunch of objections. Then we'd go back and forth, and he would be like, oh, well, I talked to this, professor of XYZ, and they came up with this solution to that thing you talked about. And I was like, oh, okay, well, that's nice, but we still have this other problem, and we'd go back and forth, and it took a very long time for me to think that this thing was feasible. And I mean, basically what happened was I ended up I think my biggest final objection to it was like, the thing is going to have to be way too long. Like, we're going to need to build something that's like hundreds of kilometers long because this system is just not very efficient. And there's nowhere on Earth you can put this thing. And he was like, well, I don't think it'll have to be that long. And I was like, well, run a simulation, run some numbers, and then we can answer this question. And he was like, he's not a programmer. He's like, I'm not going to write a simulation. You write a simulation. And I was like, okay, I will. I'll write a simulation. And so I pulled out my, Python terminal and started, NumPy and SciPy and started coding stuff up and ran some numbers and said, oh, okay, it looks like we could get to orbit with a 4-kilometer long gun. And he was like, no, that's way too short. It's going to be 10, 15, 20, maybe 30 kilometers long. It's not going to be 4 kilometers long. And I was like, look, I've got numbers. Like, I did the math. Like, I've got the physics here. And he was like, well, be that as it may, the main thing that has changed here is that you're more bullish about the system than I am. So how come you haven't joined up already? And I was like, okay, that's a very good point. It's
a pretty compelling argument. Yeah.
Yeah. It was not, that point was not actually sufficiently compelling because I still had expenses. I've got a family, and so I couldn't quit my job to go do something with absolutely zero. So Mike kept working on it, and I would help out on the garage on weekends occasionally. And then basically Mike got a direct to phase 2 SBIR grant. It was some like real money, a few $100,000. And he was like, come join me. And I was like, the thing is, I've got a really fun job. I'm building rockets. I was working at Astra, integration, manufacturing, building rockets. And I was like, it's a lot of fun. And he was like, yeah, but like, if Astra has the biggest impact it can possibly have on the world, what will that look like? And I was like, it'll bring launch costs down by a couple percent. It'll bring up mass to orbit up by a couple percent. And if I have the biggest impact I could have at Astra, because, I was, there's 100 something employees when I was there, like I will have at best, a couple percent impact on a couple percent impact. And if Longshot is wildly successful and does everything it can do, then it will have a few order magnitude impact on the cost of putting stuff in space, the quantity of stuff in space, and my impact at Longshot, obviously, as as a co-founder, as a really early employee, is going to be hopefully more than a couple percent impact on the success of the company. So much bigger impact on a much bigger impact. And I was like, okay, yeah, that's that's worth taking a pay cut for and taking some risk for and jumping into the deep end for. So that's
awesome.
Basically me joining up.
So okay, let's take a step back and talk about what is Longshot. You guys are building a gun that shoots things into space,
yes.
literally. That gun is multiple, like it will ultimately be multiple meters in diameter, like many kilometers long. And it'll accelerate via basically like timed inrushes of air, like to just propel the thing forward, sort of like a bullet.
Exactly correct. Everything you said there is correct. Yep. 2 to 3 meter diameter is about the smallest we think we could build that would still get to orbit. Things get the scaling laws are very generous to you as you get larger. So the larger we make it, the easier to get something that'll shoot into orbit. And the length of the system, I had made a lot of simplifying assumptions in my simulator. And so with, somewhat more realistic expectations, we think it probably will end up being somewhere in the neighborhood of 10 to 20 kilometers long. And there are a few places on Earth where you can build that. The test track at Holloman Air Force Base is 15 miles long. So people have built really long, straight things like this. That's a thing that people can do infrastructurally in the world. And it's not absolutely impossible. So you don't need a lot of places in the world for that to be the case in order to build the thing. A couple of them firing frequently is enough to make a huge impact in what's going up.
Is it fair to call this like Hyperloop meets SpinLaunch or something, where it's an evacuated tube? It's basically a big vacuum, and you are kinetically launching something. You're not propulsively launching something. So it's those two things combined: a vacuum plus a kinetic launch.
Yeah, I think that's a reasonable approximation. Yeah, there's a few things that are different. I think our vacuum chamber is going to be much larger than, it'll be deeper vacuum than Hyperloop and larger diameter than Hyperloop and much larger than SpinLaunch. But basically, yeah, we're imparting kinetic energy over a long distance. SpinLaunch is doing it over a long period of time. They're like, oh, we'll spin this thing up over the course of an hour or whatever, and then release it. And we're like, well, we're going to accelerate this thing over the course of like 2 seconds to go from 0 to orbital velocity plus.
That's how fast it'll go through the kilometer-long tube.
When it leaves, it'll be going about 9-ish kilometers per second, and the tube will be something like 2 kilometers, 20 kilometers long. So it'll take about 2 seconds to leave, and then about 10 seconds later it'll be in space, and then 1 minute it'll be in orbit.
How do you do the trajectory right for that? Because you have to basically, because it's going so fast that it seems like it would just, like if you shot it straight up, like it would just, is that enough to escape? I don't actually know what escape velocity is.
So we're going to fire it horizontal, and as soon as it leaves the barrel, the projectile basically use a hypersonic lift to ramp up off the atmosphere and sort of do an S curve type thing. It'll ramp up off the atmosphere to get the vertical going, and then it'll ramp back over, maintain as much horizontal.
It's like nose cone steered, sort of like the front of it actuates and can give it make that S happen. Is that how it steers itself?
For hypersonic steering, you can't have any external actuators because the whole thing is
just snap off or something.
There's the forces are too large. So what you do is you shift your center of mass. And so there's a few different ways you could shift your center of mass. The way that like ICBMs, reentry vehicles on ICBMs do it is they have some like linear actuators and they have a large mass that they wiggle. And so the cone that you've seen, like that thing sort of like just wobbles around as the mass gets moved. That requires precision actuators and like, a lot of, that is a way you can do it that is known to be a functional way to do it. We can do that if we have to. I hope we don't have to. There's a bunch of we have a bunch of cool ideas. We can go into detail on that if you want, but we have some cool ideas about that.
We'll dive into that deep later. Basically, I just want to set the ground layer of what is this thing? And
the front third or so of it will be heat shield, because when you hit the atmosphere at 8 or 9 kilometers per second, you're going to have a bad time. There's we're going to be launching close to sea level, and at those speeds, everything turns to a plasma. So the front third of the vehicle will be probably a phenolic resin heat shield that'll just ablate off and leave an arc of plasma debris in the wake. Once we're out of the atmosphere in about 10 seconds, we can release the heat shield, just pop that sucker off, and then release our payload and fire do a little circularization thrust. It'll be something like 100 meters per second circularization burn. We can use cold gas thrusters for that, or a small solid rocket motor, and then we're in orbit.
That's unbelievable. That's like that's such a fast launch. Like that's obviously so many orders of magnitude faster than normal. I mean, I think so. I'll just play like a little bit of devil's advocate just because I know that that's how you thought about it right when you were joining the company, which is like this is crazy. Like it's like it's moving, it's accelerating so incredibly fast. It's got to heat up remarkably hot. Like I know that like the Blackbird, like the SO-71 Blackbird, like that. I think the max speed of that is like a kilometer a second or something. And so it was moving
Mach 3, about a kilometer per second.
About a kilometer, so like a kilometer per second, but it was also very high when it was doing that versus like being at sea level, moving a kilometer per second is very different.
Right. It's like not quite 10 times faster.
Like it tried, and then I didn't actually realize that it shot that fast. I mean, it makes sense now that I think about it, but it's like, okay, what that means is that you have to be super, super ridiculously precise in how you're firing those, because it's like it's squeezing basically. Like as it goes along the tube, you squeeze right on it basically to keep propelling it forward. So that's got to be so precise. Like
sub-millisecond precision.
Sub-millisecond precision.
Yeah.
I mean, so it sounds like you had a lot of these concerns or whatever, or like worries when you were going into it. So like talk a little bit about the process of like getting comfortable doing it. Like what got you from initial skepticism to, okay, I'm actually going to go dedicate some serious time and effort to doing this?
Sure. So one of the first objections I had was, how the hell are we going to make some straight tube this long? Because you can't have any, like, and I had that objection initially, imagining that the projectile was sealed against the walls of the tube. But it's not. Like for most of the length of the accelerator, it's not. We start off with sort of a pneumatic gas gun. So the first, few hundred meters is like that, just to get it up to like Mach 1, Mach 2. But then you enter the large vacuum chamber and you have a lot of space around the vehicle. The vehicle is riding on rails. So then that changed the question from how do you have a tube that keeps this like perfect cross section for many kilometers to how do you keep a couple of rails solid and straight for a couple kilometers? And that second question is much easier. That's done all the time, all over the place. So that alleviated like that part of the concern for me. The question you brought up around timing of burst disks was, of timing of gas injection. The answer to that is burst disks. Like there are no valves that are large enough and fast enough opening in existence. One of the factors there is that as valves get larger, the thing that opens, like if you imagine a ball valve, you have to rotate the ball in order to open the valve. And you can go down to, Home Depot or whatever and buy a solenoid ball valve that has a little 24 volt actuator solenoid on it. And you push a button and you can open that ball valve and it'll open in like 15 milliseconds, maybe 30 milliseconds. very fast, click, 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 and the reason it can actuate so fast, which is still like an order of magnitude too slow for us, is because that little ball weighs, a few grams. If you have to actuate a ball valve that is like 2 meters in diameter, the amount of energy that it would take just to rotate that ball in place in less than a millisecond is extraordinary. And so like there's no way we could, do that. And if we're going to, at that point, rather than using like compressed gas, you have to switch over to doing something like, we've got explosives that are firing or something like that. But we like one of the simplifying things we're trying to do is make this thing as simple and as green as possible. So just compressed air, no explosives, like there's no combustion. We can do the whole thing powered by solar power. So given all that, how do you open these giant orifices for your projectile as fast as we need? The answer we found was burst disks. Burst disks are just a sheet of material that you rupture, and so we decided we would make a triggered burst disk, and that was the thing in my mind that was like, that is a technology that I can imagine us building that would absolutely scale. We can start making them 6 inches, and eventually we can make them 2 meters, and that's a thing that I can imagine us making that's not science fiction. And in terms of timing, the speed of crack propagation in a material is approximately the speed of sound in that material, and the speed of sound in steel is 5 kilometers per second. So a 6-inch disc will open in a few microseconds, and a 2-inch and a 2-meter disc will open also in microseconds. That's how fast a crack would propagate. And so we're like, okay, cool. That's, at least from a physics perspective, if we can start the crack propagating fast enough, we'll be okay. And then, can we trigger anything at that scale? Microsecond feels really fast. But if you look at things that people did even in the 40s and 50s, like with building the first atom bombs, they had a whole bunch of charges precisely positioned around the core, and they had to ignite all of those charges with nanosecond precision, single-digit nanoseconds. And so just knowing that was possible in the 40s and 50s, that yes, you can trigger things electrically with nanosecond precision using technologies from the 40s and 50s basically means like, okay, cool, this is possible. How are we going to specifically do it is a whole separate question, but that's not going to be a mystery. That's going to be a solvable
We're not
problem.
out of the realm of possibility. Like at this point, you're basically trying to figure out, does this violate the laws of physics? Like the potential solution. Yeah.
So it felt like, here is a path where we can use electrical signals that have nanosecond precision to open things that'll open in microseconds, and that gives us sub-millisecond timing for our whole system, and that all closes. That seems reasonable, and that was basically it. Then it's a matter of like engineering and sizing, and what diameter, how much mass of the payload, how much mass of the heat shield, and so we talked with one of our consultants is does heat shield design at NASA, and he helped us out a lot with simulation of that stuff, and allayed a lot of my worries around that. Anyway, so that's sort of the that basically makes the system close.
It was basically
those
like
are the big ones.
It was like can we make a tube that's straight, and timing. Those are the two biggest concerns.
Yeah, in my mind, those are the two biggest concerns I had. Yeah,
you have to get the thing up to, 5 kilometers a second is orbit. So you have to start it much ish, right?
7-8 kilometers per second is orbit. Depending on how high you are. The lower you are, the faster you are.
Yeah. Why don't you just say, taking a step back, talk about what is orbit, and how do we get things there normally versus how does this happen?
On something like a Falcon 9 rocket, you stick your payload on top of the rocket thrusts straight up. The reason for going straight up is to get out of the thickest parts of the atmosphere, because orbit is just going very fast sideways around the Earth. So you want to be going sideways fast enough that you, I'm not very good at explaining orbit. There's Scott Manley would have a much, probably a pithier way of explaining it. But if you are traveling perpendicular to the Earth and the Earth is pulling you towards it, the force of the Earth pulling you towards it will keep you, accelerating in a circle around the Earth. Like you're put a weight at the end of a string and you can swing it, and the force of gravity is the tension in the string pulling you in. And if you're going sideways, the force in the string will just keep pulling you around in a circle, and so you end up in orbit. But you can imagine if you throw a little ball straight out away from the center of the string, it won't go into orbit. It'll just fall. It's going to hit the end of the string, and then that's it. So you need to have some sideways moment to that movement to get yourself into orbit, so you're swinging around. So when a rocket launches, it goes up initially to get out of the thick part of the atmosphere, and then it ramps over and starts going sideways. And so the bulk of the speed comes once you're out of the atmosphere. You thrust perpendicular or parallel to the Earth's surface, perpendicular to your initial launch direction, and get up into the neighborhood of 7 or 8 kilometers per second at an orbit of something like 600 kilometers up, and that's like low Earth orbit. And you basically just need to go up, and once you get enough horizontal velocity, you're going to be in orbit. So we have, with Longshot, we have a sort of a challenge, which is that we're not going to be going up. So we're going to deal with the thickest part of the atmosphere for an unfortunate length of time. We can't build the thing pointing up because for basically logistical operational reasons, it's really hard to build something really, really long that isn't flat and straight on the ground. We might be able to put a very slight slope, like a 1% slope or something like that. But one of the nice things about it is if it's flat and straight, then to make it longer, we can just make it longer. So it makes it really easy to extend. Extending it means we can either carry heavier payloads or give a gentler ride to other payloads. We can do a bunch of different things if we make it longer. So we wanted to make the system extensible. So we're going to end up firing horizontal. And so then the trick is to ramp up off the atmosphere and preserve as much of that horizontal component of our velocity as possible. And so we've done some sort of primitive simulations that indicate it's probably possible, and we'll lose a kilometer per second or so to drag in the atmosphere. But that's fine. We just make up for it with launching faster. So yeah, that's sort of the.
Thinking about this, you said that you weighted it against the lasers idea. I imagine you must have traded a railgun against this idea, because that's sort of a slightly more popular, not that it's ever been done, but it's been popularly in science fiction or whatever, talked about as a potential orbit solution. So what else did you weigh this against, and why was this the winner?
I mean, the main thing that we looked at was engineering simplicity, and people have built giant guns to shoot things into space before. HARP was a pretty famous program that fired projectiles basically to low Earth orbit altitudes. And the Gerald Bull, the guy who ran that program, he wanted to put a small solid rocket motor on a small satellite and launch it into orbit there. The thing was, this was a government program. CubeSats weren't a thing yet. They hadn't been invented. They wouldn't be invented for another 20 years. Nobody had a purpose for this, and it was being done by the Army. The Army didn't care about putting stuff in space. The Air Force didn't care about putting stuff in space. There was no such thing as commercial space at that time. So the whole program was not able to be justified. And so he couldn't get it off the ground politically and economically here. So then he made some, let's say, bad choices. And he went and tried to find someone who would pay for him to build this giant gun that would be able to do this. And he found a buyer in Saddam Hussein. And so he started working for Saddam Hussein, building giant cannons. And then one day at his apartment in Belgium, some gentleman from Mossad showed up and gunned him down.
I had no idea that that's how the harp story ended. Oh my god.
Yeah. So yeah, Jerome Bull made some bad choices. Don't build super weapons for dictators. That's
good. That's a good rule of thumb. That'll help you in life. I'll write that down. That's the list. Yeah.
Jeez.
Oh my god. Well, they built that was like a traditional gun, right? Like it was a big explosive charge at the end of a sealed tube or whatever. Like what was why not?
It took two World War II battleship barrels, like stuck them end to end with some duct tape and baffles, and that was hard.
I love that.
There are people still trying to do similar things. Green Launch is trying to do a light gas gun that would be pointed up, and I think there's another couple companies that are doing similar things. The challenge with those is that the G loading on the projectile is very high, something like 10, 20,000 Gs. And what that means is that, you can't send delicate things up to space. And when you think of satellites are not really known as like super robust things. Like when you picture a satellite, you picture these like, delicate
spindly
solar arrays and
yeah.
The antennas, the unfolding antennas and stuff. Yes, they feel spindly and lightweight because they're, you need to optimize for mass because it's so expensive to put things up there. So, and electronics is, reasonably robust, but not insane. And so we're with Longshot. The nice thing is that rather than having all of your acceleration happen in the first millisecond, you get, almost 2 full seconds to accelerate, which doesn't sound like much, but compared to other accelerators, it's a lot. So we can drop our average acceleration down into the neighborhood of 600-700 Gs, which still sounds like a lot, but it's survivable by most electronics. Like your phone will totally survive. When you drop your phone from 6 feet and it hits the pavement, that's a multi-hundred G, maybe a kilog of acceleration that it experiences when it hits the ground. And most phones will survive a drop from 6 feet. You might crack the glass or whatever, but it'll work. And I mean, I guess I don't know if you saw this from the recent the airplane that lost its door, right? And then they recovered 2 functional cell phones dropped from 16,000 feet. So one of them wasn't even cracked. So modern electronics can totally survive a few hundred Gs. Hitting the ground from 16,000 feet. It'll be gentler than that. Modern CubeSats and even small sats probably won't even require much modification in order to fire in a Longshot system. Things like deployables will probably have to be specially designed, and you'll have to consider packaging and stuff. But 600 Gs is eminently survivable by modern systems. And if the cost of launching is a couple of orders of magnitude less per kilogram, then okay, you add some gussets, you make some parts out of steel, and you increase your mass by 10%, and then you're still
that's okay.
A couple of orders of magnitude cheaper. So yeah.
So that's
even if you have to pot all your electronics, it's still cheap.
It's sort of in the middle between like the gun and the like railgun, because gun accelerates you in milliseconds, railgun accelerates you over the entire length of the thing.
Right.
So, but I don't think we actually ever got there. Like, what are the reasons not railgun?
Yeah. So railguns. The main thing is that no one has built a railgun that has fired anything at orbital velocities. People have built gas guns that have fired things at 16 kilometers per second. You can go do that right now. There are, in academic labs, there are places where you can fire a light gas gun and shoot your little metal slug at 16 kilometers per second. So people have known how to use light gas and in general, pneumatic systems to accelerate projectiles up to ridiculous speeds for decades. Railguns are still an ongoing area of research and development. I know that the Navy has built some railguns, but they're expensive. There's rail erosion issues. It's not at all clear how to do this in a way that's sustainable. So from a risk perspective, it's just much less risky to try and do something pneumatically than using pure electromagnetism.
Guns do this by rifling, right? Like they'll induce a spin in the bullet so that it's not just like tumbling randomly when it comes out of the barrel. I imagine that with your center of mass thing, you can't rifle, or do you rifle?
We can't rifle. We are riding on rails, so we keep the orientation straight.
It's just that entrance into the atmosphere, that first entrance. Like, I imagine that is very important, because if you have, do you have like a breach at the very end of the barrel too, or something that happens right before you?
There will basically be a large mylar sheet to retain the, well, I don't want to say mylar specifically, but there will be a large thin plastic sheet membrane that will, that the vehicle will just punch right through.
I just imagine that first second, or first like whatever, tiny amount of time right after it leaves, right after it hits the atmosphere. It's like, okay, let's make sure that it's going exactly straight, or else the thing's just gonna like tumble immediately.
Well, we have to have control on it. The thing is, it will have a huge amount of momentum. So getting it to change its momentum, will be hard. And it will be very pointy. So basically we'll have aerodynamic stabilization. And we have to have some form of control on it, in order to get it to follow the trajectory. So hypersonic stability isn't, trivial, but part of the magic of our system is like, it's going to be very cheap. We will be able to do lots of hypersonic testing very cheap. That's our stepstone from like garage prototype to orbital launch system is a hypersonic testing platform. And that's sort of the next stage of the company is where we're looking at right now. Is we have our prototype in the garage, and then the next thing we're going to build is a 1 kilometer long system in the desert that we can use for hypersonic testing. That's where we will learn those lessons about how do heat shields work, how do we do guidance, a bunch of stuff around that. Along with, there will be a bunch of, stuff related to the accelerator, of course, but that's also where we plan to learn lessons about projectile design, manufacture, guidance, etc.
All right, awesome. So let's talk about the business then. So that's actually a perfect transition. Ultimately, what you want to do is get things to orbit as cheaply as possible. So can you talk a little bit just about how cheap it could conceivably be if it's all working?
Yeah, absolutely. The crappiest system we think we could build that we would put stuff into orbit, we think we would end up having to charge somewhere in the neighborhood of $500 to $800 per kilogram. So that's about as crappy as it would ever get. And then from there we can make things better and get down in the neighborhood of $10 per kilogram. That's sort of our target price. And we sort of joke that our current pricing strategy is going to be, we'll just take whatever other launch providers are out there, and we'll just take whatever their current price per kilogram is and drop a zero off, and that's what we'll charge. And I think at that, I think there would be plenty of room there for us. I know Elon has talked about Starship being like $500 a kilogram. I think it's going to take them a long time to get there. I mean, it'll take us, a while to get where we're going to, but I'm not too worried about competing on them with cost. I think we're going to be just fine.
Because yours is literally your only costs, assuming that not taking a little tiny fraction of the system depreciating or something, but like your normal costs are just electricity.
Yep.
And the projectile.
And
you can't reuse the projectile, but otherwise it's just a bunch of electricity that goes into these things.
Heat shield material, yeah. And we have some models. The vast bulk of the cost of launch is compressing the gas. Even if we did things like pulling the vacuum is a tiny fraction of compressing the gas.
Oh, really?
Yeah. The volume of the vacuum is much larger, but the delta pressure is much less. So the amount of energy it takes is a lot less. So even if we include things like, all of our metal burst disks, if we include the energy cost of melting them down into molten steel and reforging them, that energy cost is still also a small fraction of the cost of compressing the gas. It's there are other costs. There's going to be things, personnel costs, et cetera. But the things that cannot be removed that cannot be automated, the costs that cannot be removed are basically energy costs, and they're not much. It's basically just running some pumps. We can run them off a giant solar panel field. So that's, it's a one-time expenditure or a low we'll have to, repair and replace things periodically, but it's
Right. Yeah. Yeah.
Largely a one-time expenditure that then just use it until, it pays for itself.
Could you ultimately offer different kinds of orbits with this thing? Like, I imagine you would install it equatorially or whatever, take as much advantage of that as you can. But in theory, like, it's just however you can build that long, like, you can't, you're not going to point your thing differently. That would be too hard to do. But
we've talked about this. There's a few different ways we could do this. And I don't know, this is getting into sort of like cool, fun, speculative territory, but there's a few ways we could do it. One is, yes, we could just build, multiple cannons, at different azimuths to get into different orbits. Sure. That doesn't take advantage of our core transformation of the world, which is having orbital access be, tens of dollars a kilogram. What if we operated a set of space tugs that used liquid propellant? Because we can refuel them for nothing, right? Like, we're going to have to put ballast on our projectiles. So, yeah, you want to go to orbit? Sure, no problem. We fire you up there. 1 minute later, you're in an equatorial orbit, and then a couple minutes later, you dock with a space tug that refuels from the projectile and takes you, again, with another like 2 to 5 minute burn. You're in whatever orbit you wanted to be in, and then our tug drops you off and then goes back to its equatorial coasting orbit. And we can have a fleet of tugs up there, and we can refill them for nothing, and we can launch them for nothing, and we can use like most space tug services that people have like talked about, use ion drives and things like that, because it's they can't afford to just burn liquid propellant up there. It's expensive. It's hard to refuel. Like, that's expensive. But for us, it's dirt cheap. So why not?
That is cool how it changes the calculus so significantly. Like there's a lot of rules about space that break basically once you have $10 a kilogram to orbit. Like you could literally you could bring Dasani water bottles up to the space station, and like our astronauts can stop drinking recycled water.
One of the things we joke about is like, what if instead of designing a $100 million moon rover, you just buy a Kubota tractor and then convert it to space use? And it costs it weighs 10,000 pounds. Who cares? Who cares? That costs $100,000 to launch. That costs as much to launch as it does to buy. That's fine. Just
that's funny.
put space, pull the rubber wheels off and disassemble it a little bit so that in a way that the astronauts can put it back together. But yeah, what's wrong with having a?
And then you can fly the diesel up there too. That's the other part.
Sure, yeah.
You need to be electric.
You can. Well, I don't know if your diesel engine will run in an airless environment, but but yeah, you convert it to electric, get an electric tractor, and stick it on the moon. I'm sure people will have electric tractors in a few years. They'll be doing lithium-ion battery conversions for their tractors and stuff. Somebody's probably doing that right now. Buy an electric tractor and put it on the moon.
I want someone working on space diesel. I know it's not physically possible, but I want it.
Awesome. Hydra diesel or something, hydrogen diesel.
There we go.
So
let's talk about the stages of the business then. So you hinted that there's a middle stage there, which is basically like hypersonic testing. So right now we're in like literal your garage in the parking lot demo stage. The ultimate stage is like a huge multi-kilometer long, like massive orbital system. How do we get from here to there? Like, are there multiple steps in the middle? Like, you want to talk us through that transition?
We think there's one step in the middle. The one step in the middle is a hypersonic test system in the desert. That's basically an accelerator capable of taking something like 100 kilograms to something like Mach 10, and that provides a good test bed for us to learn more about how our system scales and do a whole bunch of hypersonic testing. And there's a lot of customers, both commercial and DoD, who are interested in doing hypersonic test. If you want to test a payload right now, a hypersonic payload, a sensor system, a heat shield, then your options right now are basically either like put it on a rocket sled or use a rocket. And the rockets that you're going to use are going to cost $1 million, and your test sled is, booked up. And there are things you can do with like wind tunnels if you only care about short durations, or if you have a very small scale system. But if you want to fire something, if you want to test a 100 kilogram system that, at Mach 5, Mach 8, there's not a lot of options that are inexpensive. And so we think we could build this system in the desert, and we could do a test shot for less than $100,000, and that's a pretty compelling value proposition for DoD and commercial.
I think it's one of my favorite facts about when they were first doing the supersonic planes is that they didn't have supersonic test capabilities before they did it. So they basically or at least they didn't have transonic test capabilities before they did it. So they were like, we could test the supersonic stuff, we can test before, but we can't figure out how to build a wind chamber that doesn't explode when we make it transonic. So we're just going to see what happens. You see these great graphs that show it's going up and then it's going up, but then there's just a gap in the middle. There's literally no data right around transonic. And so it's does it asymptote and we all explode? No one really knows. Right. We'll find out. Good luck, Chuck Yeager.
Yeah, go. Right. Yeah, X-15. Have fun. Right.
Yeah. We'll drop you. So this you're eliminating that. You're preventing the maybe we're probably not going to put a person in your hypersonic test chamber. That would accelerate too fast.
No. Yeah. The humans will never go up on our system. If you put anything biological in there, it will get sorted by mass. Your bones will be at the bottom. And that's not how most people want to emerge from their transport. But the thing is that for every human that we want to send, to space, even here on Earth, Hawaii, my co-founder Mike uses this example a lot. Hawaii, for every individual, imports something like 10 tons of stuff from the rest of the world per person per year. And they get free air, They have sources of water and food locally, and they still import 10 tons of stuff per person per year. So on the moon, that's going to be 100 tons of stuff per person per year, or Mars. It's going to be, we're going to need tens to hundreds of tons of stuff per person. So yeah, send the people up on the rockets. Absolutely, that's rockets. G-loading can be moderated enough that humans can survive. And then all the crap that the people want to, their iPhones and, life support equipment and water, air, all that stuff can all go up on cannons. And it'll be so much cheaper to resupply and make human colonies on the moon and Mars or asteroid belts or wherever, just space station, all that stuff can be much cheaper if we shoot it up there rather than by launching it on rockets.
Totally. Okay, let's hop into the tech. Let's go a little bit deeper. Let's talk about the iteration that you've been doing as you've been getting more confidence and actually building stuff and testing things out. So I don't know. We talked about a couple of these things earlier. I'm happy to start wherever you want, just in which piece of the system you want to talk about in terms of how you iterated and got it better through versions. What are some good examples?
Sure. So let's talk about burst disks, because that's a thing that is sort of critical to the company's success and was the thing that was sort of risky and has been a huge challenge, and that I don't want to say is totally resolved, but we now have a path forward. So we started off with the idea of, cool, we'll have these steel sheets and we will just pop them. Now we can't, in order to pop them with the precision that we need, mechanical options are basically out. So the thing that we envision is we've got a pressure vessel with, say, 1,000 PSI, then a burst disk, then vacuum. And so our burst disk has to hold back 1,000 PSI, and then when we push the button, it has to open. So there's a lot of ways that we have thought about and a lot of things we've tried. So one of the first things we tried was we thought we would just do a exploding bridge wire. which is basically a butterfly-shaped piece of metal that we would stick to the back of the burst disk, and we would dump a capacitor through it. It would explode, and that little pop would pierce the metal, and cool, there we go. Then we're, it's open. And that didn't work. Basically, if you know much about explosives, like if you have a firecracker sitting in your hand and you light it, it'll go just fine, and it'll pop, and your hand will feel nothing. And that's basically what was happening. We were sticking this bridge wire to our hand, and despite the fact that there's 1,000 psi of air here, it was just blowing out into that volume. Nothing happened. Okay, cool. So the problem there is that the energy isn't really getting coupled into the burst disk. The energy is just getting dissipated. Okay, cool. Well, what if rather than arcing across this little wire, we had a wire in contact with the burst disk, and we just dumped the energy directly into the burst disk. Okay, so we tried that. We charged up a capacitor, and we had a tungsten electrode. Now, one of the tricky things here is that the burst disk starts off flat, and then you pressurize it with 1,000 psi, and it bulges. So when it started off flat, we had an electrode, tungsten electrode, and it had to be spring-loaded, basically, so that as the burst disk bulged out, it would follow the burst disk. And then we dump a capacitor through this connection. And like that works, actually. That does work. We popped a lot of burst disks that way. I'll show you. Hang on 1 second.
Cool.
So the burst disk looks kind of like this, a sheet of steel. We score it so that we know where it's going to pop. And this one was pressurized, so it would start off flat, and then we pressurize it. And so it's bulging out a little bit. And then when you discharge your tungsten electrode, it definitely has an effect on the metal. And this one, it didn't pop, but this one, it did. So you can see the little scorch marks there, and it just flowers open. And there's a flange here that's holding it. That's why these are sort of like kinked there. They're folding out around the flange. So we had to bend them back in to get this off of the flange. But so we popped a lot of these, dozens, maybe hundreds. The challenge that we had was timing, because we started off when we first tried doing it, like with this one, we were like, oh, it didn't pop, dang. Well, let's make the metal thinner. We'll score it closer to its limits. And so there's a lot of there are challenges there. So you want there's some amount of control we have over the pressure in the pressure vessel. We can't control that to within 1 psi, but maybe we can control it to within, say, 50 psi. So we need a burst disk that will not pop at 1,000 psi, but is close to popping. It's got to be pretty close. And then we put enough energy into it to let it rip open and pop. So we want something that will not pop at 1,000 psi, but will pop at 1,100 psi. So it's close to its limit. So that requires some machining tolerances and a lot of testing. So we popped, again, dozens, maybe hundreds of burst disks, machining the grooves to various depths, trying different materials. And so we wanted the burst disks to be cheap because we know we're going to need to make a bajillion of them. So we don't want to use some, fancy schmancy stainless steel alloy. We want to use cheap, mild steel. And so the challenge is there that when it comes, hot rolled steel is not precision. It comes out different thicknesses. Every time you buy another, sheet, it's going to be a little bit different. And so there's a lot of manufacturing variation. And then our mill only has such tolerances. We can probably machine the thickness to within 1,000th, but we can't get much better than that. And it turns out that 1,000th is actually many psi of delta when you're at these pressures. So that was a challenge. And so we would have a lot of times we would get our whole system set up, we'd pressurize it, and we'd pop prematurely. And then we would, okay, fine, reset, okay, pressurize the system, cool, discharge, and it didn't pop. Okay, well, reset, and and it was balancing and riding that edge. So one of the other things we thought was like, okay, well, one way we can resolve this is we can just add more energy to the system. We had a pretty beefy capacitor, a 100 microfarads at a kilovolt. Like that's a lot of energy. It's not that much energy. We'll just add more. We'll bring the voltage up, bring the current up. Switch to 165 microfarads at 3 kilovolts. Okay, that's not quite enough. Let's put 3 of those together. Let's put 9 of those together. Let's put 18 of those together. We have a giant freaking capacitor bank. And now you've got that's a lot of energy. That's many kilojoules. And you still want to discharge in a microsecond, a single digit microseconds. So dumping that much energy in single digit microseconds isn't trivial. But we'll abstract away that problem. That's a whole separate problem. We'll talk about that in a minute. But cool, okay, we've got these, this sheet will just add more energy and then we can get it to work. And it worked. Like we had a dinky little power supply. It took all day to charge the capacitors. Literally took 6 hours to charge the capacitor bank. But we got it so that we could pressurize the burst disk, push a button, and it would pop. And we put a high-speed camera on that and recorded it and did it several times, and it would pop in 1 millisecond, it would pop in 3 milliseconds, it would pop in 12 milliseconds, 5 milliseconds, 3 milliseconds. It's all over the place. Just not the sub-millisecond timing that we were hoping for. And again, we still think the problem with that approach is coupling the energy into the disk, because what's happening inside is that as soon as your tungsten electrode, which also the tungsten electrodes started eroding, we had 1/4-inch diameter tungsten electrodes and they were just slagging. But as soon as that electrode starts discharging through this really shitty connection between the electrode and the disk, it creates a giant arc there, a hot expanding ball of plasma in this highly dense atmosphere, and it pushes the electrode away from the disk because you've got basically an explosion happening there. And so the more energy you put in, the more intense that explosion, and the faster you break the circuit. And so we would end up with our capacitor pack not fully discharged even after a failed pop. That's annoying. Like we're not coupling all of the energy into the disk. A lot of it's going into the electrode. A lot of it's going into the gas around the system. And so it was a very annoying, frustrating problem. But eventually we solved it.
That was awesome. I felt the weight of all of those failed tests and all those not burst disks. I just felt it sitting on you, and then
It was a year. We spent a year with our system, with our speed limit set at Mach 2. We were able to push projectiles down the barrel at Mach 2. We had boosters to accelerate them further, but they were not firing reliably, not firing robustly. We just couldn't get them to actually open with the timing and reliability that we needed. We thought about doing things like, okay, well, if we get lucky, then we can get our burst disks to open, and maybe if we just do 5 shots on one of them, we'll get lucky and our burst disks will open fast enough and won't fail, and we just have to get lucky once to get a good shot that gets us the speed record that we need to sort of demonstrate that our system will work. And we thought about doing that, and we decided that was not a good idea. It was just not going to be a good way to handle things. So we started looking at other things we could do. And we haven't ruled these out. These are still probably good ideas and other people could still do them. And we might still do them. But one of them is dual burst disks. So you have 2 burst disks and you have your high pressure air, and then you have, say, your 1,000 PSI. And then in between you have, say, 800 PSI air, and then you have vacuum. So this burst disk here can be very thin, and it only has to hold 200 PSI. That burst disk is going to be a heck of a lot easier to pop than this other beefy burst disk that has to hold 800 PSI or 1,000 PSI. And once this one's popped, Now you've got this burst that's designed to hold 800 psi, and it gets hit with 1,000 psi. It's just gonna go. So that is a way you could do this. We did some tests of this, and it seemed to work okay. Not quite as fast as we wanted, but it was more reliable and took less energy and seemed to work okay. But that's not what we ended up doing to get our current system. So right now we have, we were stuck at about Mach 2 for about a year, and the projectiles we were firing looked approximately like this. So we have rails that run down the length of the barrel, and we have these plastic bushings that ride on the rails on the top and the bottom. The whole thing is basically just a aluminum barbell, and it's plenty strong and it works great. I think this one weighs like 700 grams or something like that, less than a kilogram, and worked totally fine. But the lighter the projectile is, though, the faster we're going to be able to shoot it. So but this is the thing you should imagine when you think of like, oh, here's what we're shooting. So we were firing these things for a year or so, trying to get these things to go faster, trying to get our burst discs to work. And then once we got the burst discs working, we ended up firing things that looked kind of like that. We broke Mach 2, Mach 2.5, 2.6, and then we got Mach 3.6, and then we started having to figure out how we can improve things even more, because our goal is to hit Mach 5 in the system out here. And so there's a whole bunch of things we can do. Once we've got the burst disc problem solved, we can use lighter gas rather than using air. We can use helium. That will accelerate the projectile to higher speeds, or we can make the projectile itself lighter. And so we did a bunch of work on making the projectile lighter. So our current record of Mach 4.1 was made with a projectile similar to this, not exactly the same as this, but at this point, sort of every projectile sort of artisanal. But we still have this flat sheet. The gas hits the flat sheet and pushes it down the barrel, and we've just skeletonized the rest of it, made it super lightweight. Still have the bushings. These are thinner bushings, and just iso grid everywhere to make everything as lightweight as possible. We tried stuff with carbon fiber, basically making a composite projectile, but carbon fiber is pretty brittle, and so we ended up just getting clouds of carbon fiber debris shooting down the barrel. So yeah, and now we're working on a sort of a next generation. That one weighs about 300 grams, and we're working on a next generation projectile. It'll be in the neighborhood of 150 grams. And so with the burst disc solved and 150 gram projectile, we think that's our simulations indicate that should get us Mach 5. So that's what we're aiming for right now. Hopefully in the next month or two, we will be able to announce.
And
that.
You're just literally doing this in your backyard, basically in Oakland, like.
Yeah, it used to be an auto shop, and now we've converted it into a hypersonic test facility. I'm sitting. This used to be full of there used to be shelves here that had carburetors and stuff on them, alternators. This was the part storage area for the auto shop, and over there was the customer waiting area. The shop where we build all our stuff is that was the auto shop. There used to be a couple of hydraulic lifts for cars in there, and then our hypersonic test chamber, basically this long hallway, was a giant storage shed for RVs and RV parts and stuff. So.
No, I think one of the coolest parts is just seeing all the different, basically seeing you traverse the idea maze, trying to find the things that are not working. You go down all these dead ends, then eventually you find the thing that works. I think you shared with me another example that I thought it's not directly related to anything that'll be on the system, but what you were even shooting into. I think that story is really. Do you want to tell that story really quick?
Yeah. So we started off. We knew that we would have to have some target, right? And so we actually went on Craigslist and we bought a safe for $100, I think. Stuck it in the back of a truck. Brought it over here. It weighs 800 pounds. Giant, 5-foot high concrete and steel safe. And we set that thing up in front of our cannon. did our first test shot, knocked it on its butt, blew the door off, like put a huge dent in the back. We were like, oh, okay, I guess we'll have to reinforce this a little bit. Maybe we'll, so we put a bunch of sandbags in it. And we're like, we'll fire into the sandbags, that'll be great. So we fired into the sandbags, sand goes everywhere. Huge mess, terrible. Like, oh, and it further dented the back. It didn't even actually solve the problem. So we tilted the safe on its back, put like 5-6 inches of concrete in it, tilted it back up, built a wooden box, filled the wooden box full of carpet, put that in front of it, and fired into that. And that was sort of the basic thing that kind of worked. We still broke the concrete, and the carpet, the wooden box shredded and went everywhere, but the carpet captured most of the projectile, and it didn't make as much of a mess. And the box didn't completely get destroyed. So we sort of iterated on that a little bit. We put another 6 inches of reinforced concrete in the back of the safe. The safe now weighs more than a ton. It's like 2,500 pounds or something. And then in front of the safe, we have a steel box that is sort of a cage into which we put all this carpet. And so when we fire, the projectile basically ends up embedded in this carpet. And the nice thing about carpet is that it's, nylon synthetic carpet. When the projectile hits it going Mach 3, whatever, the projectile is hot, and it melts the carpet. And so it slags. And so all of these, long chain hydrocarbons just grab on and turn into giant globs and just grab onto the projectile and slow it down. And it basically ends up embedded in the carpet. And so what we end up with is we then take it all apart and pull things out. So we want to see, there's almost always something we can learn, even from a projectile that has been fired into the carpet at, Mach 3 or 4. So what we'll end up with is we'll be digging pieces out of the carpet that look like this. So,
wow.
So you can, like, this is the back of the projectile, and this is where the bushing would be. And so on the front here, there is ISO grid, and there's, pieces of aluminum. You see all the carpet that just, flakes off. So, here's another, like, okay, we recovered this. So this one, we're always trying to figure out, like, why did a projectile would break up in the barrel. We want to know, did it break up, before it got to some junction or whatever anyway. So there's a bunch of stuff we could learn. We started painting the sides of the projectiles so that when we caught them on high speed, we could see, which piece of this, when it's coming out the barrel in several pieces, what's the orientation of it? Yeah.
Cool.
So, yeah, here's another big chunk of the back of the projectile, just, caked with carpet. So, yeah, that's from a testing perspective, it's really nice to not have to clean up as big of a mess, I guess, each time.
Not a sand explosion or a safe exploding.
Right.
Wow, that's awesome. What was and you got the high speed camera, right? Do you have your own high speed camera now that like helps you look in the barrel?
Yeah, we have two cameras. They're both cheap, crappy high speed cameras. I don't want to say crappy. They're a few $1,000s. Kronos is the brand. They work great for us. The resolution isn't that great, but we only need 10,000 frames per second, which is it's a lot, but it's not a lot by high speed camera standards. But that's plenty for us, and so yeah, it works pretty well. So we have two cameras. One of them is color, one of them is black and white. The black and white gives slightly higher resolution, slightly higher frame rate. But the color one, there's some things that, color gives an ineffable quality. There's something about seeing at the end of the barrel, there's a Mylar burst disc. And so before the projectile comes out, it's compressing the little bit of gas that's in the barrel. It compresses that gas up against this Mylar burst disc. And as you know, when gases get compressed, they heat up. So you can see on the high speed, you can see the burst disc bulge and then turn orange as it's heating up. It's getting superheated gases behind it, and then it sort of busts open, and all these little orange Mylar fragments go flying, and then the projectile comes shooting out. And you can see the little flash of orange at the front of the projectile as it, there's a little, shock wave at the front of the projectile and as it goes by. So there's something, seeing that in color is it is different than seeing it in black and white. You can see that it's glowing in black and white, but in color you can actually like see the orange. It's more visceral.
That's got to be your like brand identity. Yeah. Those
it's pretty cool.
Superheated glowing gases or whatever the hell. Yeah, I love it. So one other curiosity I have just before we kind of conclude here is just about how you know when to fire the accelerators, the pincer maneuver. When to execute the pincer maneuver. When to light the boosters, basically. Like when, how do you know? Because it has to be so precisely timed. Like how do you know when to fire each one of those as it goes down the barrel?
Right. So right now, what we have is a set of photo gates. So we want our boosters to fire just behind the projectile. So as the projectile comes down the barrel, we have an LED and a photodiode, and the LED is continuously illuminating the photodiode. And when the projectile obstructs that, we can basically see the photodiode stops providing current, and that goes into an op amp and into a set of circuits that triggers the cascade of firing the high voltage system that discharges the capacitor that pops the burst disk. So there's a whole series of things, but it's basically a light gate. There are commercially available systems like that, but they all had delays built into them for some reason. Like Keyence has systems like that available, but they have like a 16 millisecond delay in them. And we were like, no, we want nanoseconds of delay. We want analog. We want now. So we built our own. There was a lot of iteration there in getting things robust enough. One of the challenges is that if you're firing air will have some moisture in it. Our pump tries to remove some of the moisture from the air, but there's always going to be something left in it. So when we do the discharge, you're firing high pressure air into a vacuum. As the air expands, it cools, moisture, condensate comes out, and you end up with a cloud inside the barrel. And the cloud, at least in principle, could block the light from getting through. So we need to make sure we have a bright enough LED and a sensitive enough photodiode that just reducing the intensity of the light by a little bit isn't enough. You have to actually obstruct it. And so there's a surprising number of little gotchas. Reality has a lot of detail in it that makes it some gas is going to leak around the projectile and get ahead of it and have exactly that's going to happen. And so we can see the effect of gas in the system. When we fire dry nitrogen, we see a different we have DACs that are sampling the photodiode and seeing what it's seeing as we do a shot, and we can see the difference between firing dry nitrogen versus firing air. The photodiode does get slightly obstructed when we fire air. So you have to make sure that works.
Let's talk about, at the very beginning of this, you were not sure that this idea was going to work. You basically were not convinced, and your co-founder had to convince you to even try.
Right.
What parts of the system are you very confident in now that you're we figure this out, versus which parts of it do you still feel we still have much more testing or more uncertainty to deal with?
I think there's a lot of the stuff that I know will work is going to be burst disks. That's going to be the thing that we are going to focus on. There are still some questions about the most efficient ways to make them and the best ways to make them, but we have come up with a technology that basically works for us. So I think that's the thing that I feel confident on. But there's going to be a lot of there's a long tail there of making that effective. One of the things that I am concerned about, but is basically guidance, hypersonic guidance. And there's a bunch of ideas that I have that are really cool. There's a whole rant that I could go on that I don't have time for. But there's a toaster out there called the Sunbeam toaster. And if you on YouTube, there's a YouTube channel, Technology Connections, I think, and he does a great rant on the Sunbeam toaster. And I strongly recommend watching that. The quick gist of it is, Sunbeam toaster is designed and built in the 50s. When you think of a toaster, you probably think of something where you push down the lever, and what you have inside is you have some sort of solenoid actuator to pop the toast up and down, and you have some sort of timer. and the Sunbeam toaster has neither. And it doesn't have a microcontroller. It has there's no electronics in there to speak of. The whole thing is a solid state analog computer that outputs toast. And that is how, in my mind, that is an incredibly elegant design. And I would love for our projectile to be a solid state analog computer that outputs orbit from you. The input is this projectile is at this velocity, and then it hits the atmosphere, and as the heat shield gets ablated, we could dope the heat shield to have it ablate more in one area rather than another, and that could cause our center of mass to shift, which could cause us to change our trajectory. And then once you get through that layer of doping, you get to a different layer of doping that changes your trajectory again. And so that would be a very cool set of technologies to exist. I don't know if they exist. I don't know if we can do that, but that would be really cool to not have to have active guidance on our projectile. We just make sure that the projectile is exactly the same every single time, and it's completely passive, and it just hits the atmosphere, and it goes where it needs to go. And then once we're in outer space, sure, you pop everything off, and then maybe you need to do some active intelligence stuff. So there's ideas that I have around things like that that would be really cool to make. And is that going to work? I don't know, but it'd be really cool. So there's other things like that I wouldn't say I'm bullish on. That there's a lot of risks out there that we can still take to make things really efficient and really simple. The best component is the component you don't have to install. So the best system is the system you don't have to design. Make the whole system ridiculously simple and elegant. But that's also counter to prototyping philosophy. It takes a lot of work to make that system. It's actually a lot simpler to design a system that has some actuators and a big mass on it that you can wiggle around. Like that's a thing that you can grab a few controls engineers, recent grads or whatever, and say, hey, here's the dynamics for the thing. Stick some actuators. Tell me how fast they have to be. Transfer functions and blah blah blah. And it's very much by the book, design that could be done. And so which way are we going to actually go? I don't know, but we've got a few years to figure it out.
You clearly have knowledge across many different disciplines, how do you describe yourself as an engineer? Like, are you a generalist engineer that just knows a bunch of different, you consider yourself a generalist? Like, how does one become an engineering generalist?
Be okay with being crappy at things. When I decided I wanted to learn how to make circuit boards, I was okay with, I'm going to make some bad decisions on the first circuit boards that I make. And one of the first circuit boards I designed was a 14-layer board that was quoted at $17,000 to fabricate, because I didn't know that 14 layers was a lot and that's hard to do. But seeing that confronted me with I'm not good at this. I need to there's no way we can do this. And then I had to go learn a bunch about how are PCBs actually made, because I learned the tool to make the PCB. I learned KiCad, and I watched tutorials and okay, cool, here, I'll make the thing that I want to make. And then I learned that manufacturing that is not good. Okay, well, why is this hard? I went and looked into how to manufacture PCBs, and then I learned a lot about how that works. And so I'm totally okay being crappy at something. My first weld beads are absolute garbage, but if you are okay being crappy at it, I think that's an Adventure Time quote, being crappy at something is the first step to being kind of good at it. Write some really crappy Python code for a genetic algorithm to design drone trajectories or something, and it'll be bad, and that's okay. And also, don't be afraid to look at the fundamentals. It's okay to download somebody else's autopilot for your drone, but also don't be afraid to make your own autopilot. Don't consider it a waste of time and effort to try and do that. Spend a few weeks on it and figure out why it's hard, and then you'll probably come up with ideas about like, oh, that's why they had to do this way. And, you know, if I use their autopilot, then how did they solve this problem? You know, give you a lot of context for how other people are doing their things. So do crappy, bad versions of things as a hobby project. And then, you know, eventually you'll probably get good at some of them or enough of them. It'll give you context so that when somebody tells you something about the system is impossible, you can be like, I don't know about that. You know, I did a crappy hobby project that did 90% of that, so it can't be that hard.
Have you tried to, on that note, have you tried to make a toaster yet? The perfect analog toaster?
No, I haven't tried to make a toaster. Yeah, I think I don't really care too much about consumer products. I don't know.
You'd rather spend your time on space than toast?
Large infrastructure projects, civilization-changing infrastructure projects, mega projects. I want to work on a Dyson sphere or something. You know, that's more interesting to me.
That sounds good.
I'll build one in my garage. You know, deploy it from my garage, and then well.
There we go. Perfect, man. Well, Nato, thank you so much. This was awesome. I had a lot of fun. This is a great conversation. So thank you so much for joining.
A pleasure. Absolutely. It was a lot of fun.